Thank you, Cindy. Thanks for the introduction. Welcome, everybody. Good morning to those of you on the West Coast, and good afternoon to everyone calling in from other time zones. So I'm going to be talking about intermediate Linux and shell scripting today. Before I get started, I just want to address a question that's come up a few times regarding the sharing and reuse of the materials. So the PDFs of our presentations, they are all available online. And for those of you who would like to reuse any of the materials, feel free to do so. If you want to teach some of the content at your own institution, or if you wanted to incorporate into a class. The one thing we ask though is that you retain the attribution. So if you're using the entire presentation, we have a slide in there describing the complex program. And if you just wanted to use select material, you'll notice that the footer now contains the funding information, specifically the name of the project and the NSF funding. And finally, just a reminder that that all of the PDFs are available, not just today's, but the entire series, available in the link that I just posted into the chat. So with that, let me go ahead. I'm going to share my screen and get started. Okay, so my name is Bob Sinkovits. I am the Director of Education and Training here at the San Diego Supercomputer Center. And today I'm going to be covering intermediate Linux and shell scripting. One thing I want to add is, we've done this presentation a few times and we realize there's a lot of content. In the new year, we are going to be splitting this into two presentations. One where we actually go a little bit deeper into some intermediate Linux topics, and then we're going to take shell scripting and split that out into a separate talk, because we realize that there's really a lot to cover there. So as a reminder, that this program, Complex, it's a new, well, it's been close to a year now, SDSC program, where we cover all of the non-programming skills that we think are essential to effectively using supercomputers. And as I mentioned earlier, this is supported by the National Science Foundation through the through OAC CyberTraining program. All right, so just a rundown of what we're going to be covering today. You're going to get a quick introduction. We're going to talk about the file system hierarchy, symbolic links and hard links, redirection and pipes, wildcards and globbing, aliases, command history, navigating between directories with pushd popd, environment variables, configuration files, pseudo-filesystems, and then a very quick introduction to bash scripting. If you had downloaded the PDFs earlier, let me ask you to re-download, because this morning I had made a few updates and added a couple additional slides covering the topics of single quotes, double quotes, and backticks. So, this session, we're going to say it's for anybody who works in a Linux environment and wants to acquire the additional skills to more effectively use advanced CI. In the Linux world, intermediate is in the eye of the beholder. So everything that we're covering in this session would be considered basic or elementary by Linux systems administrators. But we figure that you're probably not a sysadmin, rather it's more likely that you're a student, educator, or a researcher who uses advanced CI as part of your work or studies. In which case, I'm going to say that these topics really are intermediate in the context of Linux users as opposed to Linux professionals. And just a few prerequisites. We already assume that you know a little bit about Linux, that you've logged into a system like Expanse or Bridges or Stampede. You kind of know your way around at least a little bit, that you can list files using the ls command, that you know how to remove files with rm, that you can navigate between directories with cd, you can look at the contents of a file, you know how to use one or more of the standard editors such as vi, vim, emacs, or nano, and that you have at least a rudimentary understanding of relative and absolute paths. Okay, so we're going to start off with the Linux file system hierarchy. This is a little bit of an abstract topic, but I feel that it's still worth covering because it's going to say, just helpful to understand the layout of a Linux file system. So you're going to find that there are some variations among different Linux flavors or distributions, often called distros, but they tend to be pretty minor and mostly related to the lib bin, user lib, and user bin directories. So as a regular user, not a sysadmin, you don't need to know too much about the file system hierarchy standard, but we're covering it here to just round out your knowledge, make the Linux environment a little less mysterious. Now, if you want to learn a little bit more, I have some links on this slide, a couple of overviews, one on Wikipedia and one from Linux Journal. And then if you want to do a deeper dive, I have a couple of other articles that you could read. So under the FHS, we have some standard directories where you can reliably find some expected content. So /home is where we're going to find our user home directories. So if you've been on one of the access allocated systems, again, like Expanse or Bridges or Stampede, you've logged on, you're familiar with your home directory. It will have a name like /home/your username. We also have bin and user bin directories, and these traditionally contain the essential and some non-essential command binaries, respectively, but these are often merged. So if you're on a system like system like Expanse, where we're using CentOS flavor of Linux, /bin is going to be a symbolic link to user bin. And when I say the essential and non-essential commands, these are the things that you're probably already familiar with, like ls and rm and cd and so on. Now there are directories at the top level called /sbin and /user_sbin, and these contain binaries of commands that are mostly used by the systems administrators. And like bin and user bin, these are often merged. You'll find a lib and user lib directories, which contain libraries needed by the Linux commands and utilities. And again, these are often merged. And /opt is where software was traditionally installed, but with the rising popularity of package managers like SPAC, which we do use here at SDSC, and I know it's had a lot of uptake at the other supercomputer centers, this directory is not used quite as much anymore. We have /etc. This contains configuration files for Linux shells, schedulers, networking, accounts, package managers, and others. If you are building or compiling your own code, you'll find often that the C and C++ header files will be found in /etc. /root is the home directory for the root user. Var is where we have log files. Dev is device files for terminals, disks, networking, etc. Under the Linux philosophy, everything is a file. So in fact, even things like your terminal is considered a file. Proc and sys are pseudo-filesystems that we're going to touch on very, very briefly that contain information about running processes and hardware, and /temp is a location for storing temporary files. Now, not everything fits into the FHS, and this is especially true in a high-performance computing environment. And one of the reasons I bring this up is I mentioned the opt directory, which is where software had traditionally been installed. You're going to find that /opt, especially in an HPC environment, is not used as often. Our software, I'm going to the third bullet here, our software is installed and managed using something called SPAC, and you're going to find that the applications that we build and maintain are now going to be found in /cm shared apps SPAC. We also have large parallel file systems that do not fit into the FHS. And examples that you might be familiar with are /expanse, /lust or /projects, and expanse, lust or scratch. And then finally, we provide hybrid cloud storage as a paid service for some projects, and this is going to be mounted at Expanse projects. Okay, so moving on to symbolic links and hard links, and I think this is some information that you're going to find much more relevant for your work. Symbolic links and hard links give you a way to refer to a file or an inode, and I'll talk about inodes in the next slide or two, by a different name. And these are very useful when you want to avoid writing out a full or relative path name every time, or if you want to have a generic executable name that refers to a specific version. And we're going to discuss the differences between symbolic links, also known as soft links, and hard links in the next few slides, along with a little bit of background on inodes. Now, both types of these links, hard and soft, are created with the Linux ln command. So if we want to create a soft link, we'll use ln-s, followed by the file name that we want to link to, and then the name of the soft link. And if we want to create a hard link, it's going to be again ln, no additional flags, the name of the file, in this case file2, and then the name of the hard link, in this case hard-file2. So if we're working with symbolic links and hard links, it's useful to know just a little bit about inodes. So an inode is a data structure that stores information about a file system object, such as a regular file or a directory. So you could think of the inode as containing metadata, where the file itself would contain your data, but the inode would contain information such as the permissions, the read, write, and execute permissions for the owner, for the group, and for the world. It contains the file size. It tells us who owns that file. It will have timestamps indicating the last time that the file was accessed and modified. And it also contains the location of the data in the file system, but not the actual data itself. So a file is a link to an inode, and a hard link is just another file that links to that same inode. So an inode is only deleted when all the links to it have been deleted, and if the original file is deleted, the data can still be accessed using the hard link. A symbolic link you could think of as just another name for a file. So if the original file is deleted or removed, this symbolic link still exists, but it can no longer be used to access that data. So in the next few slides, we'll try to make that a little less abstract. So let's imagine we have a directory. It contains two files, file1 and file2, and we're going to create a hard link to that first file using ln without the -s option, and we're going to create a symbolic or a soft link to the second file, ln-s file2, file2.soft. So we're going to use ls with an option that you're probably not familiar with, the -i option to list the inode number. And you're going to see that file1 and file1-hard both have the same inode. That these are referring to the same location, to the same file. File2 and file2soft, they have different inodes. Now notice what happens if I remove the original files. Now if I try to list the contents of file1-hard, we will see that it still exists. So we actually had a copy of that file. Now when we look at the contents of the soft link, we'll see that there's no such file or directory. Now, which one should I be using? Symbolic links or hard links? I'm gonna say that 99% of the time, you're gonna work with symbolic links since they have a few advantages over hard links. First of all, they let you span file systems and can be created even if the file being linked to does not yet exist. So you might be wondering why you would want to do that. It's actually very, very convenient because that way you can set up and create an environment in anticipation, say, of software being installed. So let's do, we're going to try creating links to files that don't yet exist. So I'm going to do ln file3, and I'm going to try to create a hard link. Now recall that our directory just included the files, file 1 and file 2. Here we're going to get an error, no such file or directory. Now when we try creating a symbolic link, ln-s file3, file3.soft, you're going to see that there was no error message. Now in the second example, I'm trying to create a hard link across file systems. Let's say I'm currently in my home directory and I'm trying to create a link to a file that exists in Expanse, Lust, or Scratch, Sinkovits, my username, file 4. We'll see that I am not allowed to do that. And I get the error, invalid cross-device link. If I try doing the same thing with a symbolic link or a soft link, you'll see that there are no errors and it actually worked. And now when I execute ls, I will see the hard links that I was able to create and all of the soft links. So let me just take a look at the chat very quickly. Okay. All right, so moving on, we're going to talk about redirection and pipes. So this may be a topic that you're a little familiar with. We might go just a little bit deeper today. So most Linux commands and utilities, they're going to write to standard output, usually abbreviated as stdout, standard out, which is the terminal if you're working on the command line. Output can be redirected to a file using the greater than symbol, and if you use two of them, it's going to append output to a file. So let's look at a simple example. Let's execute the date command and redirect the output to a file that we're going to call out file. If I look at the contents of that file, you'll see the output of the date command. Now, if I run that same command again with a single redirect symbol, date greater than out file, I concatenate the contents of the file, we'll see that it's been updated. The output has been overwritten, but if I use two greater than signs, we're going to see that output is appended. And I should add here that you can use the append option for files that don't yet exist. So let's say you're developing scripts and workflows. You don't need to worry about using a single redirect the very first time you write into that file. If you want to accumulate output over the course of the job of the script, you can just start off with the two greater than signs and begin by appending to an empty file. Now a pipe takes the standard output from one command and it redirects it to the standard input of a second command. And an arbitrary number of commands can be connected using pipes. So let's say that I wanted to count the number of files in the current directory. I could do ls-1 so that I get a listing of all the files in a single column. And then I can pipe that into the wc, or the word count command. And here I'm using the -l option for the number of lines. And we can see that in the directory where I executed this that I have that I have 13 files. Let's say I wanted to list the 3 longest jobs running on one of the Expanse compute nodes. In this case, I chose exp2-09. So I could run the sq command. I could pipe that into the grep command. So I'm using grep to search for the string exp-2-09. And then I can pipe that output into head-3. And by taking these 3 commands, stringing them together using Linux pipes, I could easily list the 3 longest running jobs on that particular Expanse node. Now, standard in can also be directed. And I find this is really handy if you want to prevent a command from listing the name of the input file. So in the example below, we avoid having to pipe output from wc into the cut utility. So let's say we just wanted to know the number of lines in a file. We can do wc-l file1.txt, and here we'll see 9 followed by the file name. Now I can use the Linux cut utility Little more complicated. I take the output of WC, I pipe that into the cut command, and then I select just the first field. But a much easier, much more convenient way to do this, and let's say that we were executing a script where we wanted to capture just the number of lines in the file, I could have done WC-L, and notice now that I'm using a less than sign to redirect file1.txt as the input into WC-L, and now I'm going to get just the line count. Okay, moving on to wildcards and globbing. This is incredibly useful capability in Linux. It allows you to do operations on multiple files. If you are working on a Mac, which has its own flavor of Unix, Mac OS, that this wildcard and globbing will work there too. So when you're on a Mac, you can always use the GUI. You can open up multiple windows. You could drag files around. You could delete them, and so on. But if you're trying to do operations on sets of files that match certain, where the names match certain patterns, you're going to find that it's kind of difficult. And even there, you might want to open a terminal and start working at the command line. So wildcards allow you to express a pattern for matching multiple file names using any combination of the following. So a question mark is going to match any single character. An asterisk is going to match any string, including the empty string. And if we use the square braces, we can use that to match multiple characters or ranges of characters. Now, globbing is the operation that expands the pattern into a list of files. And globbing is done automatically by many Linux utilities that operate in files, such as ls, rm, mv, cat, head, tail, and file. So we'll show a few examples. So imagine we go into a directory. I execute ls and I see these 24 files. Oh, and let me add that these examples are all in the GitHub repo that's listed on the title slide. So if you want to play around with these on your own after we're all done, I really encourage you to do that. So I look in this directory and I've got these 24 file names with a range of names, abcde.txt, some random collections of letters. We'll see that there are a few files with names like file 1, file 2, file 3, file 4, file A, B, C, and D.dat. So let's say that we wanted to list just the file names that match a certain pattern. So we could do ls file star, and that's going to list just those files that begin with the string file. Now, if we wanted to list all of the files that began with an F, in that case, we could have used ls f star, and now you're going to see, in addition to file 1 through file 4, file A through file D.dat, that we also picked up some additional files, such as fgij.txt, fxhij.exe. And if I wanted to find just those files that contain the name GHI, I could do ls asterisk GHI asterisk. So notice that we can use multiple wildcards in a single expression. And here we ended up listing efghi.txt, exghi.exe, and ghijk.txt. Notice that that last file, it begins with GHI, but our expression was ls star GHI star. And as I mentioned in the previous slide, the asterisk can also match the empty string. And that way, that's how it was able to pick up the ghijk.txt. Now, if we want to match single characters, we can use the question mark instead of the asterisk. In the language, what we call regular expressions, the asterisk is greedy and it will try to match as much as possible. When we use a question mark, it restricts it to a single character. So let's look at a few examples. So if we do ls file question mark dot dat, that's going to list all of the files with names in the form file, followed by any character, followed by dot dat. In the second example, I'm combining the question mark and the asterisk. So here I'm looking for files of the form A, followed by any single character, CDE dot any string. So in this case, I pick up abcde.text, axcde.exe. And then finally, last example, I'm looking for file names that contain any 5 characters, followed by a period, followed by any character, followed by an X, followed by any character. Okay, there's a question here from Haley. If I would like to delete a large number of files with similar names, can I use wildcards within the rm command? Yes, you absolutely can. So here we've been restricting ourselves to listing, but we could have used rm here also. So let's say, look at the second example on this slide, that I wanted to delete all of those files that had names in the form file question mark dot dat. I could have replaced that ls with an rm. Now I will say though, just be a little careful, and I'm going to give a really, really good example of using aliases in a few more minutes, so that your rm command aliases to rm-i, so you don't accidentally do an rm star and remove everything. But yes, you can use it there, and you can also use it in many other Linux commands. Right, and we can also do implement wildcards and globbing using the square braces. So in this case, we're going to look at 4 different examples. Again, starting off with the same collection of 6 files in our directory. So let's say that we wanted to list all of the files that were of the form file, followed by the numbers 1 or 3, followed by dot dat. Excuse me. So here we do file and then in square braces 1, 3, dot dat. So what I'm doing here is providing a list of characters that we're going to match. So in this case, we picked up file1.dat and file3.dat. Excuse me a minute. Now we can also match ranges of integers. So let's say I wanted to pick up file1, file2, and file3.dat. I don't need to type all of that out explicitly. Say my square braces 1, 2, 3. I could instead do, within my square braces, 1-3. So now we're going to be doing multiple matches using a range of integers. So in this case, we pick up file1, file2, and file3.dat. We can also do multiple matches using lists of letters. In this case, we wanted to see files that started with A or C, followed by X, followed by range characters dot range characters. In this case, we pick up axcde and cxefg.exe. We can also do that same match using a range of letters. In this case, if I replace the AC with an A-C, instead we're going to pick up all the files that begin with A, B, or C, followed by X, followed by any number of characters. Let me just check the chat again. Okay. All right, so now we're going to talk about aliases. So aliases are just shortcuts for Linux commands, and these are really useful for keeping out of trouble. For example, accidentally deleting all your files and abbreviating complex commands. So I am going to recommend, if you haven't done this already, that you create an alias for remove. And here I'm going to use the alias command, alias, followed by rm equals, and then in single quotes, rm-I. So now, when I do which to see which remove command I'm executing, we see that it is aliased to rm-I, and it's using the user bin rm command. So we talked about user bin and bin at the beginning of this talk. Now, you might be wondering, you say, well, you know, I'm never going to do an rm or rm star, but you could do it accidentally. So let's say I wanted to remove all of the files in a directory that ended with .exe. Normally I would do remove space star.exe. But if I had a typo in there and I did remove space star space .exe, now it's first going to expand that asterisk to all of the files in the directory, and then it's going to look for a file named .exe, which is probably what you didn't want. So, you know, this is a great example of how an alias can keep you out of trouble. More often, you're going to use aliases to abbreviate long commands. Say things that you are executing over and over, and it could be not just a single command. It could be a series of commands that are piped together. So sometimes I like to get on Expanse, and I need a reminder of what are the properties of all the partitions or the different queues that I could run in. You know, the shared queue, the compute, the GPU shared, and so on. Now the slurm commands have lots of options. Sometimes I don't get the output formatted just the way I wanted it, but I did a little bit of experimentation. I'm not going to go into the details here, but I had a sinfo command that I formatted just the way I wanted, and rather than having to type sinfo-o and then in quotes %15p %6a, this very, very long cryptic command, instead I could create an alias, and in this case I'm calling it partitions. Now, after I created that alias, when I use the which command, I see which partitions, and I can see that it is aliased to the to this rather complex command, and that it's executing the sinfo command found in cm shared app slurm current bin sinfo. Aliases, all of your aliases can be listed by typing alias without any arguments. Years ago, I didn't know that there was an easy way to get all this information. I would try to remember what were all of the aliases that I created. So if you just type alias with no arguments, you're going to see a listing of all of your aliases. So you can see I start off, I have a couple here that I use for slurm. I alias remove to remove-i, and so on. I even set up a couple of aliases at the bottom here to get an interactive core or a node on Expanse. Okay, so we're going to move on to command history. So you can inspect your command history using the history command. You can do this using the arrow keys, or you can execute or modify a previous command so you do not have to remember or type everything again. You can also search your command history using Emacs key bindings, for example, Control-R for reverse search. And there are special commands to execute previous commands. So in the most basic form, we would type history on the command line, and you will get a long list of the commands that you had executed. I'm not showing them all here. I just restricted this to the last three. So I could see that I executed ls file star.txt, I removed a file, and then I did echo hello. Now, if I want to execute the last command again, I could use 2 exclamation points, bang bang, and that would, in this case, execute echo hello. I could have also used the arrow to go up 1 to select that command and then just hit return. More useful is I could execute the last command that started with a particular string. So let's say I had a, I had previously used ls ls filestar.txt. If I just do bang ls, what's going to happen is my history is going to be searched, going backwards, looking for the most recent command that started with ls, and then it's going to execute that. And I can also execute a specific command by number. So let's say that I wanted to execute command 428. I could have listed my history, gone back there, done a cut and paste in the command line, but even easier, now that I see that command 428 is the one I want to execute, I could just do bang 428 and it will execute that command. All right, navigating between directories with pushd and popd. So sometimes you will want to maintain a stack of directories, and I realize that this example was a little abstract. Then the next time I redo my slide deck, when we divide this into intermediate Linux and shell scripting, I'll try to make this a little more informative. But you could use the pushd and popd commands for navigating between directories. So pushd adds a directory to the stack, popd removes it from the stack, and dirs lists the current contents of the stack. So you might be wondering why you would want to do something like this. Imagine that you had logged into Expanse or Bridges with Stampede, and there are things that you want to do in different directories. You want to go into one directory where you are say building your executable, modifying it, recompiling. Another directory, say where you're executing it. So we can put these directories onto the stack and we can move back and forth between them with pushd. So let's say I do start off with pushd directory 1. Now we're going to see that I have a stack. Let's say I'm starting my home directory in a subdirectory called ppdem. So you can see that ppdem dir1 is at the top of the stack, followed by ppddm. I could push another directory on top of that stack. If I do pushd without any arguments, it's going to swap the top two elements on the stack, top two directories. If I do pushd with a number, it's going to bring that directory to the top. If I just want to get a listing, I could do dirs. If I want to pop directories off the stack, let's say I don't need them anymore, I could do a popd. And if I want to pop a particular directory, I could use an offset, in this case +1. Again, a little abstract, but I'm going to say if you go to the GitHub repo, play around with this, I think it's going to make a little more sense. And like I said, in the next version of this presentation, I'll give a more illustrative example. Okay, environment variables. This is something that I think you're going to find really helpful. In Linux, we have shell variables and environment variables. And they're very, very similar, but they have some subtle differences. So these allow you to customize your environment and control how applications behave on a Linux system. So shell variables are only known within the current shell. Environment variables are known globally, and they're going to be inherited by processes and shells that are launched by the current shell. You're generally going to want to use environment variables rather than shell variables. Shell variables are set using the syntax name equals value. Space is not allowed around the equal sign, and by convention, these shell variables are going to be capitalized. They don't need to be capitalized, but it's going to, I think it's going to make your shell scripts a little bit easier to read. Shell variables are made into environment variables. Again, so that they're known globally and inherited by other processes using the export command. A time when you would, a very concrete example of when you want to do this is when you're writing batch scripts, Slurm scripts, you might want to create variables in there that are then available to the job that had been launched. And the value of a shell or environment variable is accessed using the $sign followed by the variable name. So let's make this a little more concrete. So let's start off, we're going to create a couple of shell variables. We're going to name them key1 and key2, and we're just going to set them to the strings ABCD and EFGH. Now we're going to export key2 so that it becomes an environment variable. In the next line, we're going to combine the two steps of defining and exporting. So here we do export key3 equals, in this case, a string ijkl. Now, if I want to see what the value is of that variable, I could use echo followed by dollar and the name of the variable. So echo $key1, echo $key2, echo $key3. Now, if I launch a new shell within this shell, say bin bash, if I do echo key1, we're going to see that we get no output. Key1 was only known in the parent shell. Whereas key2 and key3, these were made environment variables so that they are known globally and they are picked up by the child shell. So in this case, we can do an echo key2, echo key3, and we see the values. Now, another way to assign shell and environment variables is to use the declare command. Using the X flag to export. Another common option is -R to make the variable read-only, at least within that current shell. So here, using the declare command, we can say declare var1 equals ABC, declare -X, var2 equals DEF. If we create a child shell, like we do below, var1 is not known by the child shell because it's just a shell variable. But var2, since we use the -X option, is an environment variable. Where these shell and environment variables are going to be used a lot is configuring your environment to use software. So I recommend, afterwards when you work through these exercises, that you look at the contents of your path and lib variables. And these are going to be updated as we use the module facility to install software into our paths. Okay, actually I have a few examples here. Yeah, so all of your environment variables can be displayed using the env command. And I'm showing some partial output here. So you can see that my path variable contains paths to a number of different directories. Library path is also set. Man path, this is the path to man pages. You can see that my login name, log name, is set to Sinkovit. I can see the shell. I can see my home variable. Okay, configuration files. So Linux has a number of configuration files for customizing your environment. Etc profile, etc bashrc, a .bash profile and a .bashrc in your home directory, and others. And to make things even more confusing, there's a hierarchy of scripts. Scripts can execute other scripts, and some scripts only apply to the login shell. Fortunately, you can usually get by with just two general rules. You're going to customize environment variables in your .bash profile, and you're going to put aliases and functions into your .bashrc. Okay, an interactive shell is one that reads from and writes to the user terminal. So if you can enter commands at the command line and see output, you're in an interactive shell. This is probably what you're most familiar with. So let's say that you launch a shell using SSH locally, or when the new shell is launched with the login option. This is where you're usually going to work. An interactive non-login shell is launched from the login shell by executing bash at the command line or opening a new terminal from the Linux desktop. A non-interactive shell is not associated with a terminal. It's usually launched by a user executing a script or associated with an automated process. Okay, order of execution of these configuration files. What I show here in orange are things that are maintained by the sysadmins. You don't need to worry about it. The ones in blue are where you're going to customize your environment. So to start off, when you log in, the Etsy profile is going to be executed, and it is going to call it's going to call a series of other configuration files, an Etsy profile.d and the Etsy bash rc. These are things, again, that you don't need to worry about. Then the .bash profile in your home directory is going to be executed, and it is then going to call .bash rc. If you're in a non-interactive shell, it's a little bit simpler. Just bash rc is going to call the Etsy bash rc. Now, the bad news is if you do internet searches looking for information about the relationship between the Linux configuration files, you'll probably come across figures that look like this. It's a little overwhelming. But the good news is if you're using bash, which is the standard Linux shell nowadays, it's going to be your default when you log on to any of the access allocated resources, you're probably just going to need to worry about two files, bash profile and bash rc. Use bash profile for commands that should be run only once, such as customizing environment variables. So if you look in your bash profile, you're going to see some content at the top, which is going to be there by default. I'm going to say do not edit that part. Those first three executable lines, if-f bash rc, then so on. You absolutely need that. You don't want to mess with that. Below that is where you could start adding your customization. So you can see here that I'm making some customizations to my path variable. The bash rc is where you're going to define commands that should be run for every new shell. So again, the content at the top is going to be there by default. Don't edit that. Below that, you can make your customizations. And this is where you could put aliases, or you could also load modules that you want to be within every shell. So you can see here that I alias the remove command to rm-i, copy to copy-I, and so on. Just mention pseudo-filesystems very, very quickly. In Linux philosophy, everything is a file, and Linux distros provide pseudo-filesystems that allow you to access dynamically generated content using the same tools that you would use to access regular files. And these are normally found in the proc and sys directories. Now, a reason you might want to use these is, say, to get information about the system that you're running on. So let's look at the file /proc/cpu-info. And I recommend that this is something you do after we're done here. I'm just showing the first few lines, but this is where you can get information about the hardware, the type of processor that you're running on, the clock speed, the number of cores, the amount of memory, and so on. Okay, I'm going to switch gears now. We're going to talk very, very quickly about bash scripting. As I mentioned at the top of the hour, for 2025, we're going to be taking this talk and dividing it into two sessions. One covering the content that I've gone through already with a few additional topics, and one where we go just into shell scripting. So, given that we only have about 6 to 7 minutes left, we're going to go through this very quickly. Think of this more as a reference that you can go back to. So shell scripts are programs that are executed by the Linux shell. They can contain comments, simple commands, and programming constructs for loops, branches, variable assignment, and so on. Scripts can be run in three ways. You could make the script executable. For example, you could change the permissions. In this case, I set it to 755, and then I just type the name of the script. I could use the source command followed by the name of the script. In this case, it does not need to be made executable. Or I could use dot followed by the name of the script. So shell scripts can be as simple as a list of Linux commands. The first line the hash followed by the exclamation point is usually pronounced shebang, defines the shell that's going to be used. It's a good idea to set this, but if you forget, you're normally going to get the bash shell. So on the left, I show a very, very simple script. I'm just using echo, head, tail, and the WC commands. So let's say that I wanted the script to list the first lines of a file, then list the last two names of the file, and then finally the number of lines in the file. So when I execute this, you'll see that I get listing first two lines of the file 1.txt, followed by line 1 and line 2, then the last two lines of the file 1.txt, lines 8 and 9, followed by the number of lines. So again, all we were doing here was using echo to print out strings, and head, tail, and WC to get some information about the file. But I took all of this and I just combined this into a single package. Now, before we go any further, we should say a few words about quotes. Linux has two types of quotes. Single quotes preserve the literal value inside the quotes, and double quotes recognize the special meaning of characters like dollar, single quote, backslash, and exclamation point if you have history expansion enabled. So here we're going to define two environment variables, var1 and var2. And then I'm going to do echo, and within single quotes, $var1 plus $var2. And the result is probably not what I was expecting. You see that I got the literal string, $var1 plus $var2. If I enclose this within double quotes, so now we recognize the special meaning of that dollar sign, so we get the value associated with that variable. Now we get ABC plus DEF. Linux also has backticks, which are something completely different, and they capture the output of a command. And this is going to be really useful when you're developing shell scripts. So here I create two variables, me and date. And with me, I capture the output of the whoami command. And with date, I capture the output of the date command. And then I can interrogate the contents. So I used echo $me, echo $date, and you can see that we captured the output of whoami and date. All right, we only have a few minutes left, so I'm not going to go through these in much detail, but just be aware that Linux does have Linux shell scripting allows you to iterate, to create arbitrary loops. Most often you're going to use that to iterate over the items in a list, and these lists can be defined in multiple ways. So here, a little bit of a contrived example, but I'm looping over all of the files in a directory, and I'm getting the line counts. We could have just done wc-l filestar.txt more simply, but this is just to illustrate the loop. So I could do for file name in filestar.txt. I could have captured the output of ls, or I could have listed all of the file names on the on the line containing the for statement. All three of these produce the same output. We can also iterate over ranges of numbers using the sequence command or the curly brace notation. Shell scripts can accept command line arguments where $1, $2, $3, and so on store the first, second, and third arguments. $0 stores the name of the script. This, if you've done any programming in C or C++, this is the same convention that those languages use. Using command line arguments can make your scripts much more flexible since you don't need to hard code content. And again, not going through the details here, but if you look on the right-hand side, you'll see that we were able to pass the arguments file1 or file2 to our script. I'm just going to skip over that. Let's see, I have a question here. Okay. Shell script can also contain conditional statements. Just like most programming languages, we have if else, or if else constructs. And we can do comparisons both on integers and on strings. And let me just skip over these. Yeah, so we're out of time. Like I said, next in 2025, we're gonna split this into two topics. But let me just wrap up. Say, if you want to learn more about shell scripting, go ahead, work through the examples that are in the accompanying GitHub repo. You can also follow these links to get a little more information. So just to wrap things up, again at the top of the hour, learning intermediate Linux skills are going to help you become more effective user of advanced cyber infrastructure. Hopefully this tutorial provided you with the tools to customize your environment, automate tasks, and create some simple workflows. And while we've covered most of what we think you need to know, there are many resources on a wide range of topics in case you need to go deeper. And with that, I am going to wrap up, and I am happy to take any questions.